In this video, we're going to take a look at some examples of Kruskal's algorithm in action. So we're going to be finding minimal spanning trees. So our first example, we're just going to find a minimal spanning tree and its total weight or total cost. Okay, so we have this weighted graph right here. This is not a tree. As we can see, we have many circuits, for example. So step 0 over, let's go through Kruskal's algorithm. We know that this is a connected graph. So let's go through, and first things first, or step 0, is just to draw in all of the vertices again, and try to keep them at the same relative spot. Trying to keep the same overall shape that we have here. Okay, next we're going to find our very cheapest edge on the graph. So I see we have a 1 here. Do we have any other ones? Yeah, we have another 1 right here. We don't have anything cheaper than a 1. And that looks like everything. Yeah, so those are all of our 1s. So we can choose either AC or FG. Doesn't matter which one you choose, you will get a different graph, but it will still be minimal if you do everything else correctly. So I'm going to choose FG. You don't have to do that, but you could. And so, in fact, now, well, we've chosen FG, so FG is out, but we still have this 1, we still have this AC, and if I draw it in, that doesn't make any circuits. So I can actually have both of them. So if I picked AC first and then did FG, or FG first and then did AC like I did, it doesn't matter. Sometimes, like we saw in the first example, last video, the first example with Kruskal's algorithm, sometimes if I pick one, that will block me from doing the other, but that doesn't happen here. And so now our next cheapest looks like it's going to be 2. And so we've got AB and DC. So again, neither of these look like they're going to be creating circuits. So I'm going to pick AB. And I want to try to put in this other 2. And I can do it because when I do that, I don't get any circuits. So now, after 2 comes 3. I have a 3 here. And that's my only 3. But I can't draw it in because if I do, I'll get a circuit A, B, C, A. I'll get this circuit here. So I can't do this 3. This 3 is out. Now I've got 2 4s, which is my next cheapest. I can't draw in AD because that'll give me A, C, D, A. That'll give me a circuit. So I can't draw in this 4. Oops. I can't draw in this 4, but I can draw in this 4 because that won't create any circuits. Okay, now the next cheapest one. So there's a couple things here. First of all, notice if I separate off this E, this here is a tree. So if I look at all the vertices except for E of the edges I found, we have a tree. So if I add any edges among these vertices, I'm going to create a circuit somewhere. So whatever edge I pick next has to involve E somewhere. Okay, so it has to be this 10, 7, or the 6. The 6 is the cheapest, so that's the one I'm going to want to draw. But let's keep going with our regular Kruskal's algorithm and forget that for the moment. Keep that in the back of our heads. So I just drew this 4. I can't draw the other 4, so I have to move on. The next cheapest one is going to be 5. This one here. But if I draw this 5, then I'm going to get this FD. I'm going to get another circuit, F, D, C, G, F. That'll give me a circuit here. So DF is out. I can't draw it. So after 5 comes 6. I have a 6 right here. And like we saw before, like hopefully keeping it in the back of our minds, we have to draw, no matter what we draw, it has to be an edge connected to E. And of the edges connected to E, 6 is the smallest, so that's going to be the one we want. Okay, and notice we have 1, 2, 3, 4, 5, 6, 7 vertices, and we've drawn 1, 2, 3, 4, 5, 6 edges. So now this subtree, or the graph that we've drawn, is connected, has 7 vertices and 6 edges. So that means it's a tree, and in fact, that means we have a spanning tree. So this is a minimal spanning tree. And notice this is going to be our only minimal spanning tree because we never had any choices. Well, we did have some choices. Like, for example, we could have drawn this one first and that one second, or we could have drawn that one first and that one second. But no matter what, we were always going to draw both of the ones, both of the twos. And of the two fours, this one, AD, was always going to be blocked off. So no matter what we did, we were always going, no, sorry, no matter what choices we made for this graph, we always would have ended up with the same minimal spanning tree at the end. So there's only one minimal spanning tree for this graph, and its total weight is 1 plus 1 plus 2 plus 2 plus 4 plus 6. 1 plus 1 is 2. 2 plus 2 is 4. 2 plus 4 plus 2 is 6. 6 plus 4 is 10. 10 plus 6 is 16. Okay, so there's only one minimal spanning tree, and its weight is 16. You can't do any better than that. Moving on, let's do a slightly larger one. So find a minimal spanning tree and its total weight. Okay, so again, step 0, I'm going to just draw in all the vertices, none of the edges. Okay, and now that I've done that, I want to find whatever the cheapest edge is. So I see some 2s here, I see a 4. Do I have anything cheaper than a 2? Just scanning the graph, I see I have a 1. And so I'm going to draw that in. So now my next cheapest ones are going to be this 2 and then this 2 here. So I don't know if I can draw both of them. I'll just draw this BD first. That doesn't create any circuits. So if I draw the FG, that also won't create any circuits. So I can draw them both in. Now, do I have a 3? Maybe doesn't look like I have a 3, but I do have 2 4s. And so again, this is kind of the trickiest part, is not creating any circuits. That's maybe a little more visually easy to tell, but it's the thing to be careful of, where I see a lot of mistakes, is you have to make sure you're actually finding the next cheapest edge. Right? If I had gone right to this 6, well, then I would be ignoring this 4 and this 4 here. So make sure you're scanning the graph and finding what's actually the next cheapest thing. So if I draw this BG, then that's a 4. It looks like I don't have any circuits. And then I can draw a H, which is also a 4. And once again, I still don't have any circuits. So then what's the next cheapest? Well, I have this 6 here. Do I have any 5s? Doesn't look like I have any 5s. Go fish. If I draw this DF, well, then I get a circuit, because then I can go D, F, G, B, D. So I will have a circuit if I draw this 6. So I can't draw this 6. DF is out. After that, we've got DE and BC. So it looks like I can draw BC. Can I draw DE? Well, if I do that, then I'll get this big circuit consisting of these vertices, D to E to F to G to B to D. That's my circuit. So I can't do ED, that's out. What about BC? Well, it looks like that's fine, and sure enough, that doesn't make any circuits. So now, after 7, so those are my 2 7s. Now I've got, looks like 2 8s. And can I do HE? Yes, I can. Can I do AB? Yes, I can. But notice, if I do AB, then now I can't do HE, because then I'll have a circuit H to E to F to G to B to A to H. So I can only draw one of AB or HE. So I drew in AB. I still have this 8 HE, but I can't draw that now because that would create a circuit with this AB that I've already chosen. And so now the next cheapest one is going to be a 9, which I have one of right here. And sure enough, I can draw it in without creating any circuits. And now I'll count my vertices: 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. And how many edges do I have? 1, 2, 3, 4, 5, 6, 7, 8. So that means I have the right number of vertices and edges. Everything is connected. I have a minimal spanning tree. But this isn't our only minimal spanning tree, because we could have, the only real choice that we had that was of any consequence was whether or not to do AB or HE. So these two are our minimal spanning trees. And in fact, they're going to be our only minimal spanning trees. So if this was a question, you would only have to find one of these, but just for the example, I'm going to draw both. And now we can find their total weight. So that's going to be 1 plus 2 plus 2 plus 4 plus 4 plus 7 plus 8 plus 9. And so 1 plus 2 is 3. 3 plus 2 is 5. 5 plus 4 is 9. 9 plus 4 is 13. 13 plus 7 is 20. 20 plus 8 is 28. And 28 plus 9 is 37. So both of these have a weight of 37. And no other spanning tree of this graph will have, no other tree will have a weight of 37, and no other tree will have a weight less than 37. Okay, so this is the best, these two are the best we can possibly do. All right, now we have a bit of a word problem. So several properties need to be connected by an electrical grid. Some potential wire placements along with their costs are shown in the graph below. Find an arrangement of wires that makes every house hooked up to the grid and minimizes total cost. Find the total cost. Okay, so what we have here are houses, properties, farms, whatever. We've got a bunch of them located at different spots, say on a map. And we've got a bunch of wires that we're thinking about putting down, or cables or whatever. We're thinking about putting a wire maybe between E and G, maybe between E and F, or F and G, or E and C, C and B, etc. And so not all of these are created equal. So for example, E and D costs 15, maybe this is in hundreds, maybe this is in thousands, but DE, if we wanted to put this wire down, that would cost much more than, say, CE. So we want to be a little strategic about this. And we want to make sure every house is hooked up, but we don't want to make any, we just want to make sure everything is hooked up. We don't want to make anything more than we need to. So this tells us that we're probably going to be looking for a minimal spanning tree. And so we're going to do the same thing that we've been doing. A, B, C, D, E, F, G. Okay, so what's the cheapest edge, or rather, what's the cheapest wire placement that we have on this graph? Well, I see a 5 here. I see another 5 here. It doesn't look like we've got anything cheaper than 5. And so I'll choose AD to draw first. That's 5. And CE will also, we can draw because that doesn't create any circuits. Now the next cheapest looks like it'll be a 6, and I've got a 6 here. I don't have any other 6s, so I can draw it in, DF. Now our next cheapest ones are 7s, so we've got BE and AB. It looks like I can draw both of these. So if I draw BE first, that creates no circuits. So that's a 7. And then if I draw AB, that also won't create any circuits. Our next cheapest edges or wires are 8s. And we've got an 8 here and an 8 here. But notice if I draw BC, that will give me a circuit with B, C, and E. And if I draw FE, that will give me a circuit F, E, B, A, D, F. So that'll give me a circuit. So I can't draw either of these 8s. So they're both out. The next cheapest would be 9s. So I have a 9 here, DB, and I have a 9 here, EG. If I draw DB, that'll give me a circuit, DB, AD. So this 9 is out. If I draw a 9 here, well, that'll connect me up with G, and that doesn't make any circuits. Okay, so I can draw it in. And before I do that, that's another thing we can notice is again, if we have this lonely vertex, this isolated vertex, everything in this larger graph is connected. This is a tree, this larger graph, if we ignore G. We have a tree, so drawing any edges between these two vertices, any of these two vertices, will result in a circuit. It won't be a tree anymore because it'll have too many edges. So we'll draw this EG for 9. And this also goes to show we want it to be minimal. We don't want to spend any more money than we have to. So we could also, draw in this 8, this BC, but B, E, and C, all of these houses are already hooked up to the grid. There's already wires running through all of them. So there's no reason to make one right between B and C if we can already get electricity via BEC. Okay, electricity doesn't have to pay this toll as it runs through this. It just has to move there. And so here I'm assuming we don't have any redundancies or anything. We just want to cook everything up as cheaply as possible. And this is the way to do it with this minimal spanning tree. And so its total weight is 5 plus 5 plus 7 plus 7 plus 6 plus 9. So 5 plus 5 is 10. 10 plus 7 is 17. 17 plus 7 is 24. 24 plus 6 is 30. And 30 plus 9 is 39. So whatever our units are, maybe they're dollars or hundreds of dollars or thousands of dollars or whatever, there's no way we can make this wire arrangement cheaper than 39. And again, this graph, it sort of removes a lot of our context. It removes a lot of our data. I've drawn D and E to look pretty far apart and E and B to look closer together. That might not be the case. B and E might be really far apart, but for some reason, maybe it's just cheaper maybe you can run this wire directly, and maybe for D and E, you have to avoid a lot of terrain or something else like that. So there could be all sorts of reasons. It doesn't matter. I could have drawn E closer together, or I could have drawn them farther apart. It doesn't matter how I draw the graph. We just care about what are these labels, what are these weights. So hopefully this gives you a better feel for minimal spanning trees and Kruskal's algorithm. That's going to be all for this video.